Hi, welcome back to Principles of Communications. In this video, we will be discussing about the various types or various sections of a superheterodyne receiver. First, we have here is the RF section, and it consists of a pre-selector stage and then an RF amplifier stage. A pre-selector is a broad-tuned bandpass filter that has an adjustable center frequency that is tuned to the desired carrier frequency. What it does is that it provides an initial band limiting. Let's say that you have your input signals frequency spectrum here, and then you have a specific amplitude in this particular frequency, and you have another higher amplitude here, and another one here, and then another one. Let us also say that you are only interested in capturing the signal at this particular frequency, and the rest, just don't care about the rest. The preselector does not necessarily just isolate this particular frequency, but what it does is that it performs a somewhat rough of a filtering of the frequency in your input signal, and its primary purpose is that it prevents a specific frequency called the image frequency from entering the receiver. And I also said image frequency. We will be discussing about it later on. The preselector also reduces the noise bandwidth of the receiver and provides the initial step toward reducing the overall receiver bandwidth to the minimum bandwidth required to pass the information signal. The RF amplifier determines the sensitivity of the receiver, that is, sets the signal threshold. Also, because the RF amplifier is the fast active device encountered by a received signal, it is the primary contributor of noise and therefore a predominant factor in determining the noise figure for the receiver. A receiver can have one or more RF amplifiers, it may not have any, depending on the desired sensitivity. Several advantages of including RF amplifiers in a receiver are as follows. One, it provides a greater gain, thus it also provides better sensitivity. Number two, it improves image frequency rejection, and we will also be discussing about image frequency rejection later on this video. Third advantage is that it has a better signal to noise ratio. The fourth one is that it has a better selectivity. The second section in a superheterodyne filter, or rather receiver, is what we call the mixer or converter section. The mixer or converter section includes a radio frequency oscillator stage, or commonly called a local oscillator, and a mixer or converter stage, commonly called the first detector. And the local oscillator can be any oscillator depending on the stability and the accuracy required. The mixer stage is a nonlinear device, and its purpose is to convert radio frequencies to intermediate frequencies. Heterodyning takes place in the mixer stage, and radio frequencies are down-converted to intermediate frequencies. Although the carrier and sideband frequencies are translated from RF to IF, the shape of the envelope remains the same. Notice the envelope of the modulated signal, and then also notice the shape of the envelope of this IF signal. You have a modulated signal here, and then a local oscillator here, and um, they serve as the input to the mixer, and then the output of this mixer is what we call the intermediate frequency. It only changes the frequency, but the shape of the envelope, which we are concerned with, and which carries the information we are concerned with, is not affected. It still remains the same. Also, the most common intermediate frequency used in AM broadcast band receivers is 455 kHz. Image frequency. This is what we were talking about earlier when we discussed about not wanting it to reach the receiver stage. Why? Because the image frequency is an undesired input frequency which is demodulated by superheterodyne receivers along with the desired incoming signal. This results in two stations being received at the same time, thus producing interference. Basically, we do not want the image frequency to be received. And this is what happens. You have your mixer here, and you have the desired signal frequency here, your oscillator frequency or the local oscillator, and then the intermediate frequency which we want to get. However, the image frequency interrupts with the desired signal frequency, and when it does, it mixes with our desired signal frequency, and it creates interference or somewhat of a noise. And because we do not want the image frequency to enter the receiver, we want to reject it. And the way that we compute how much we reject the image frequency is by calculating the image frequency rejection ratio, which is given by this equation. Wherein it states that the image frequency rejection ratio is equal to the square root of 1 plus the square of our quality factor times the square of rho, wherein rho is equal to the ratio of the image frequency to the signal frequency minus the ratio of the signal frequency to the image frequency. Next is the IF section. The IF section consists of a series of IF amplifiers and bandpass filters and is often called the IF strip. Most of the receiver gain and selectivity is achieved in the IF section. The IF center frequency and bandwidth are constant for all stations and are chosen so that their frequency is less than any of the RF signals to be received. The IF is always lower in frequency than the RF because it is easier and less expensive to construct high-gain stable amplifiers for the low-frequency signals. Also, low-frequency IF amplifiers are less likely to oscillate than their RF counterparts. Therefore, it is not uncommon to see a receiver with 5 or 6 IF amplifiers and a signal RF amplifier or possibly no RF amplification. Next, we have our detector. The purpose of the detector section is to convert the IF signals back to the original source information. The detector is generally called an audio detector or the second detector in a broadcast band receiver because the information signals are audio frequencies. The detector can be as simple as a single diode or as complex as a phase lock loop or balanced demodulator. Let us recall that in the modulation part, you have a message signal here, and then you modulate it through your modulator, and then you pass it through a carrier frequency of a higher frequency. And then the output is the AM. There. And then you transmit it through your antenna, and then afterwards you then receive it through your receiver, also through an antenna. And then what we do is that we convert it into intermediate frequency, and then by using our detector, we finally convert the intermediate frequency back into our message signal. Finally, we have our audio section. The audio section comprises several cascaded audio amplifiers and one or more speakers. The number of amplifiers used depends on the audio signal power desired. Now, what happened in the superheterodyne receiver is that first we receive the signal, which is in the form of radio waves, and then our preselector performed an initial band limiting, and then the RF amplifier amplified the radio frequency to a more usable level. And then the mixer or converter section converted our RF wave or our radio frequency wave into intermediate frequency, which then passed through our bandpass filter to isolate the specific signal that we are concerned with. And then we further amplified this intermediate frequency through these IF amplifiers. And then we passed through the audio detector. And uh, what happened in the audio detector is that it converted the intermediate frequency back into the original signal that was sent to us, that contains the message that we want to decrypt. And then what happens in the audio amplifiers is that it takes as input the extracted signal from our detector, and then it amplifies that signal, and then converts it back into sound using our speaker. And there we have it. We have successfully demodulated and converted our received signal using our heterodyne receiver. Thank you. Hi, welcome back to Principles of Communications. In this video, we will be discussing about single sideband receivers. Specifically, we are going to discuss about bit frequency oscillator or BFO. BFO, it produces a frequency input to bit or mix with the IF signal and results in a sum and difference frequencies, with the result being the original audio. Note that it should have at least the tuning range of 1.5 kHz above and below the center of the IF passband. In a non-coherent bit frequency oscillator single sideband receiver, we receive the input signal here, and then the preselector makes its selection, and then the RF amplifier amplifies the radio frequency, and then the output signal from this stage directs toward the RF mixer, wherein the RF signal is mixed with the RF from the local oscillator, and then it is then converted into intermediate frequency. And then the intermediate frequency goes under amplification and bandpass filter to reduce its bandwidth. And finally, it goes into the IF mixer, wherein the bit frequency oscillator mixes the with our intermediate frequency, and that bits that bit or those bits mixes with our IF signal, and it creates a sum and difference, and the resulting signal is our demodulated information. This figure shows a block diagram for a coherent single sideband BFO receiver. This receiver is identical to the BFO receiver shown previously, except that the local oscillator and the bit frequency oscillator frequencies are synchronized to the carrier oscillators in the transmitter. The carrier recovery circuit is a narrowband PLL that tracks the pilot carrier in the composite single sideband reduced carrier receiver signal and uses the recovered signal to regenerate coherent local oscillator frequencies in the synthesizer. The synthesizer circuit produces a coherent RF local oscillator and bit frequency oscillator frequency. The carrier recovery circuit tracks the received pilot carrier. Therefore, minor changes in the carrier frequency in the transmitter are compensated for in the receiver. and the frequency offset error is eliminated.